Good afternoon, everyone, and perhaps good morning or good evening for participants participating online. Welcome to the special session of the Tsukuba Conference 2023, entitled, special session, Catastrophic Disaster Preparedness and Response, organized by the National Research Institute for Earth Science and Disaster Resilience, or NIED. My name is Shohei Matsura, and I'm the Deputy Director General of International Affairs of NIED, and your organizer for this session. We have a very exciting program for you today. But before that, I would like to invite Professor Kaoru Takara, President of NIED, to give us some opening remarks.
Thank you, Dr. Matsura. Good afternoon, everybody. I'm Kaoru Takara, President of the National Research Institute for Earth Science and Disaster Resilience. Thank you very much for joining today's Tsukuba Conference special session organized by us, NIED. The theme of this session is Catastrophic Disaster Preparedness and Response. This year marks the 100th anniversary of the Great Kanto earthquake. So catastrophic disaster is a kind of huge, very huge disaster which cause very serious damages in wider area of Japan or nation. For example, we know the Ise-1 typhoon disaster in 1959, and the Kobe earthquake in 1995, and Great East Japan earthquake and tsunami in 2011. So those disasters are also catastrophic disaster events. Young researchers from NIED who are active in disaster prevention considered such catastrophic disasters and chose it as the theme of this event. We have invited researchers from a wide range of disciplines and even from Taiwan to participate in this session. And we hope that the presentation will lead to transdisciplinary research and collaboration across disciplinary borders and across national boundaries. I believe this session will help the audience recognize the urgent need for catastrophic disaster preparedness and the importance of increasing or improving disaster preparedness through cooperation among industry, government, academia, and the private sector, including people. I have heard that the Tsukuba Conference has an established reputation for networking among young, talented people with a bright future. This session will be a good opportunity for the speakers, audience members, and those participating online to create a network for future disaster risk reduction activities. Thank you again for your joining us today. Thank you very much.
Thank you very much, Takara-sensei. Before we start the presentation, I would like to briefly introduce our speakers today. 7 speakers from NIED and a special guest from Taiwan. So maybe when I call your name, you can raise your hand so that the audience can know who you are. So we start off with Dr. Yi-Chung LIU, or we affectionately call her Dr. Gloria, from Taiwan. She's from the National Science and Technology Center for Disaster Reduction in Taiwan. And following that, I would like to introduce Mr. Satoru YUSA from the Disaster Information Research Division of NIED. Yes, he'll be our moderator for today's session and also the panel discussion. Next, I would like to introduce Dr. Tetsuya TAKEDA from the Network Center for Earthquake, Tsunami, and Volcano and then Dr. Yohsuke Kawamata from the Earthquake Disaster Mitigation Research Division. Then Dr. Asako IWAKI from the Multi-Hazard Risk Assessment Research Division. And then Dr. SHAKTI PC from the Storm, Flood, and Landslide Research Division. And finally, Dr. Tomofumi KOZONO from the Volcano Disaster Resilience Research Division. Okay, so we'll move on to the presentation, and I'll give the floor to our moderator, Mr. Yuasa.
From now on, I will serve as the moderator. Now we will move on to the presentations by the 7 speakers. We will take over very simple question by each presentation, like checking term or numbers. After the 7 presentations, we will have a panel discussion followed by a Q&A session. If you are joining us online, please enter your questions or comments in the chat box anytime. After each presentation, a panel discussion will be held to discuss future prospect and international cooperation for each research project. So now let's start the presentation right away. The first presenter is Dr. Takeda. Please take the stage, okay. And Dr. Takeda is a researcher, Network Center for Earthquake, Tsunami, and Volcano at NIED. Dr. Takeda will give a presentation on earthquake and the tsunami observation network. Dr. Takeda, the floor is yours.
Thank you. I'm Tetsuya Takeda from NIED. I'm happy to have an opportunity to talk here. Today, I'd like to talk about a new earthquake and tsunami observation network called NNET. One of potential catastrophic disasters is Nankai Trough earthquake. This photo shows Kochi City just after the latest Nankai Trough earthquake 70 years ago. Kochi City was hit by tsunami and subsided and disappeared below water. So a catastrophic disaster would generate such cities in nationwide. So this map shows distributions of our seismic network. It is called MORAS. So here, the anticipated Nankai Trough earthquake source area is located in southwest Japan. And Nankai Trough earthquakes repeatedly caused damages in a cycle of 100 to 150 years. And the probability of its occurrence is 70 to 80% in next 30 years. So estimated damage is devastating. So here, there is a blank area where seismic observation network doesn't cover yet. So we, NIED, is currently constructing new earthquakes and tsunami network called NNET here. This figure shows a schematic image of NNET. NNET system is based on inline system, which means that each observatory is directly connected in a row to the main cable. And additionally, there are 4 branches for future expandabilities. This system is designed for long life because it is not easy to repair instruments on the seafloor. So to enhance the reliability, we adopt a variety of redundancies, 2 subsystems, such as 2 subsystems and 2 landing stations and duplicated sensors. Thus, this system is designed to keep running over 20 years. So, NNet data will be provided not only NIED, but also Japan Meteorological Agency called JMA, private enterprises, and local governments. This figure shows inline observatory. The cylindrical contra is made of beryllium copper alloy with excellent pressure resistant. This is divided into 2 sections. Left section contains 2 pressure gauges for duplication. Pressure gauges two pressure gauges are exposed the same pressure as outside of vessel. So right section is pressure resistant. So this section contains instrumental measurement and optical amplifier. So this is here we call here S unit. So S unit is a core device which has many functions to measure seismic ground motion and to communicate with landing stations and so on. The S unit has 2 sets of accelerometer velocity seismographs for duplications. NNet will greatly contribute to earthquakes and tsunami detection. Left figure shows a map of the difference between the first arrival times for earthquakes with and without NNet. NNet can directly detect seismic motion up to 20 seconds earlier. A right figure shows in case of tsunami. In case of tsunami, NNet can directly detect tsunamis up to 20 minutes earlier. So NNet will provide prompt and accurate information of earthquakes and tsunami in near future. Here, I'd like to introduce collaboration with railway companies. So we have other offshore networks. So offshore network data is already used by railway companies. SNet data SNet of East Japan data and DoNet of Key Peninsula data are provided through agreement with 3 JR companies. The observed data above source regions can detect earthquakes in 10 to 30 seconds earlier than before. So the data is used to automatically apply emergency braking and stop the train. So NNet will also contribute railway safe railway operation control during shaking of the Nankai Trough earthquakes. Finally, I'd like to show a photo of a landing station in Kushima City. The landing station is connected to submarine cable pulled up from oceans and communicate with 36 NNet observatories. So the whole system of NNet will be completed in 2025. Thank you.
Thank you very much, Dr. Takeda. It was a very informative presentation. Now we'll take one question from on site or online. Of course, there is a time to take a question after the panel discussion. Is there any question? Okay, thank you very much.
Thank you.
So we move on to the next presentation. So Dr. Kawamata, the floor is yours.
Thank you very much. Thank you very much for your kind introduction. So today, I'd like to talk about a possible role of a large shaking table test facility, E-Defense, to prepare against future catastrophic earthquake disasters by introducing E-Defense history briefly. So E-Defense is the world's largest shaking table test facility, and we have Guinness World Records. And the former name is a three-dimensional full-scale earthquake testing facility, but even I forget the former name sometimes, so please call us E-Defense. So the cost of E-Defense was 45 billion Japanese yen, so it costs a lot. So we had a very, very big motivation. It's 1995 Kobe earthquake. So after 10 years after Kobe earthquake, we started E-Defense operation. But unfortunately, we had another tragic earthquake, 2011 East Japan earthquake. But the original E-Defense could not simulate long duration motion recorded in East Japan earthquake. So we had upgrade. We need to upgrade the E-Defense specification. So now we can simulate most of ground motions recorded in the both earthquake, Kobe earthquake and East Japan earthquake. So by now, we have performed 124 series of large-scale experiments, including various type of structures, like very typical Japanese house, wooden house, reinforced concrete building, steel frame building, bridge pier, and like port facility, and pipeline, and so on. We performed many kind of experiments by now. With progress of earthquake engineering, E-Defense research objectives have changed gradually. In the first phase, our research purpose was verification and development of seismic evaluation and retrofit methods, especially for existing old buildings. But after that, seismic performance of most of buildings in Japan have improved considerably, and we could reduce the risk of fatal collapse of building. So now at that time we had to move to the next phase. So now we are doing several researches to verify and develop some special tools for indoor safety because many people died due to turning over of furniture in the past earthquake. And we are developing some real-time damage assessment technique of structure. And now we need to help developing a business continuity plan by keeping a structural function. So it's the current project objectives. And in future, I believe, we have to move to the next phase, disaster mitigation for regions. We made lots of study about seismic performance of individual buildings, but we have to move to a regional disaster mitigation in future, and to consider about catastrophic disasters, that it's the theme of this session. We have to think about multiple disasters and or cascading disasters. So in the past, we made lots of research about a single structure during a single earthquake event. But in future, we have to make lots of research about multiple structures and multiple events. So it lead a regional disaster risk reduction against catastrophic disaster. So let me show some examples of past e-defense testing. So the first one is seismic retrofit for existing old wooden house. So we prepared two wooden house, and one is reinforced. Actually, we observed this kind of fatal collapse after Kobe earthquake, and retrofit reinforced house has had minor damage, but it's still there. So it means the retrofit methodology tested in this project worked very, very well. So next example is large-scale testing on indoor safety in high-rise building. So we made a numerical analysis first to calculate the motion at the higher part of high-rise building and input the motion at the higher floor to the test specimen. So we install lots of furniture and also device in the structure in rooms. So we have two dining rooms. One is prepared against earthquake, and the other preparation. You can see some tools in the prepare room. So you can find lots of tools in a home center. So if you think you don't prepare against future earthquake in your room, please stop by home center to see, to look for the proper tools to prepare against future earthquake. So the last one is a large-scale test on functional maintenance of wooden houses. So recently, newly built house has a higher seismic performance, seismic grade 3. It means seismic performance of the house has 1.3 times larger performance than performance defined in the standard. So it means the house is very, very rigid. So we have two houses. One is a base seismically isolated house, and the other is house built on the soil with sewage pipes. So because of higher rigidity of house, the house itself has minor damage, but it's likely to slip. So it's a reason why sewage facility damaged fatally, and when sewage function is out of order, we cannot use this house. It means this house lost the function. So I have 2 minutes. 2 minutes. So in Nankai Trough earthquake, the probability of subsequent earthquake occurring is much higher than usual. And in fact, we observed lots of large aftershocks in 2011 East Japan earthquake and Turkey Syria earthquake in this year. So let's make next challenge risk reduction for multiple large earthquakes. But we made lots of research about single structure and single earthquake event. But real city is a couple system of ground, structure, foundation, equipment, lifelines, and so on. And urban function worked as a network. It means very localized damage in network may induce fatal damage to urban function. But a full-scale experiment of the regional model, city model, is impossible. Even we use elephant shaking table, the largest shaking table, it's impossible. So we need a numerical analysis technology, but we need verification and validation, evidence-based verification and validation to verify the numerical analysis technology. So we need accumulation of evidence under various conditions. But of course, catastrophic disaster will not wait for our preparation. So the question is how to accelerate accumulation of evidence in this quite limited time. So let me propose about international interlinked data set, construction of a data set. So each research group made their own research and upload all the research data in the sharing system, and we can share the data. So everyone in this project can use this data to verify their own research. So let me summarize. I think we need data accumulation to verify the advanced technologies, but accumulation data set take quite a lot of time. So but we have to prepare against future catastrophic disaster as quickly as possible. So let's work together and let's make great collaborative research in future. Thank you.
Thank you very much, Dr. Kawamata. It was a very exciting presentation. Now we take maybe one question from on site or online. Do you have any question about this presentation? Okay. There is a question from online. The question is, when you say mitigation in a region, do you mean the sum of strengthening individual buildings in the area, or do you mean some kind of mitigation for the entire area?
Mitigation for entire area. So it's a reason why I didn't mention in my presentation because shortage of time, but so a city is couple system, so we worked as a network. So but simple combination of individual structure is not, I cannot estimate the damage to regional damage. So entire area, entire area, yeah.
Thank you very much. So is there any, okay. So thank you very much, Dr. Kawamata. So next, we move on to the next presentation. I would like to introduce the next speaker, Dr. Iwaki. Dr. Iwaki is a researcher, Multi-Hazard Risk Assessment Research Division, NIED. Dr. Iwaki will give a presentation on seismic hazard assessment. Dr. Iwaki, the floor is yours.
Thank you, Yusa-san, for introduction. So first, as an introduction, Japan is surrounded by potential source areas of megathrust earthquake, as we all know. And Nankai Trough earthquakes have repeatedly occurred with about several tens to several hundreds years intervals in the history. And not only the megathrust earthquake, we also have to take care about the active faults. There are numerous active faults in the inland part of Japan islands that can potentially cause destructive shallow earthquakes. For example, 1995 Kobe earthquake and 2016 Kumamoto earthquake. So the focus of this talk will be the current status and issues of prediction and preparedness for the future seismic disaster in Japan in terms of seismic hazard assessment, which is my research field. Seismic hazard assessment is the quantification of the ground motion intensity level with associated uncertainty. And this is achieved by assembling the research results from all fields of seismology and related studies, including the earthquake source studies and earth structure itself and wave propagation and etc. And using these research results, we make ground motion prediction shaking maps and also the probabilistic seismic hazard assessments, that's called PSHA. And these contributes to the damage estimation of the buildings, economy, etc., and also the risk assessment and management and response measures. So let me here mention a little bit about the importance of the seismic observation. The various kinds of observation systems, including the ocean bottom observation that Takeda-san just introduced in his presentation, many kinds of observation systems provide essential data for earth science studies. And well, one example is that at the time of the 1995 Kobe earthquake, the number of the observation stations installed in Japan was not enough to represent the heavy damage area in Kobe City. That's colored in red color here. It's called damage belt. So, and after the 1995 earthquake, the number of the observation network has increased drastically. And these two figures compares the number of the strong motion observation stations before the 1995 earthquake and the present. And this enhancement of the seismic observation was helped by the establishment of an organization called HERP, Headquarters for Earthquake Research Promotion, as a special governmental organization to sufficiently apply the results of earthquake research to general public and disaster prevention organizations. These two figures are the major products provided by HERP. That is the seismic activity and long-term occurrence probabilities for the major active faults in the middle and also the subduction zone earthquake. So as a product of long-term evaluation and strong motion evaluation of HERP, the first national seismic hazard maps were released in 2005. So in our research project in NIED, we contribute to development of these seismic hazard maps. So the national seismic hazard maps have been continuously updated and improved every year, adapting the state-of-the-art evaluation and research results. And these are used not only in the academic fields, but also the many fields in industry. And our seismic hazard map is also installed in global seismic hazard map by global earthquake model. So this is used by many researchers and industry from all over the world. So now I will talk about some major revisions we have made to the National Seismic Hazard Map after the occurrence of the 2011 magnitude 9 Tohoku earthquake. This earthquake was very huge, and it exhibited unanticipated natural phenomena, including the earthquake magnitude itself, and also the resulting ground motion and tsunami, which was underestimated before the earthquake. So at this earthquake, we learned how we had not known about anything about this earthquake. So major revisions have made to the seismic hazard maps based on the lessons from this earthquake, including the seismic activity model, and also the ground motion prediction model, and also the representation of the hazard information to the public. So based on these lessons, we make ground motion predictions for anticipated subduction zone earthquakes, including Nankai Trough earthquakes. Considering the uncertainty of earthquake source model, that means we run several hundreds of large-scale simulations for many various earthquake scenarios with different size of the earthquake, which means the magnitude of the earthquakes are very different from one to another, and also many patterns of slip distribution. So it's because we don't know what kind of earthquake or the size of the earthquake for the next coming Nankai Trough earthquakes. So this 2016 Kumamoto earthquake was another example that made us realize the importance of considering the uncertainty of the earthquake before the prediction, when making prediction. So this 2016 Kumamoto earthquake was the first and currently the only earthquake that actually occurred at what is called major active faults evaluated by Hertz in the National Seismic Hazard Maps. So before the occurrence of the earthquake in 2014, the HERP have actually evaluated this earthquake fault with length of 24 kilometers and the magnitude with 6.5. But after the earthquake, by analyzing the observed data, the magnitude was estimated around 7.0 to 7.1 by many models proposed by many researchers. So we had to say that the fault model evaluated before the earthquake underestimated the actual earthquake in terms of length, width of the faults, and also the seismic moment, which is the magnitude of the earthquake, and consequently the resulting ground motion intensity. So this is another important lesson that we have learned. So in summary, establishment of the HERP headquarters of this earthquake research promotion after the 1995 Kobe earthquake accelerated the seismological research and its application, including the enhancement of seismic observation. That was very important. And the first national seismic hazard maps of Japan was released by HERP in 2005. However, the 2011 Tohoku earthquake was an anticipated huge event. So based on the lessons from this earthquake, major revision was made to the national seismic hazard maps. And also the 2016 Kumamoto earthquake exhibited another example of underestimation of the strong motion evaluation. So the important thing is we need to consider the uncertainty of both the natural phenomena and our knowledge on not only about the earthquake, but any kind of natural disaster. Thank you.
Thank you very much, Dr. Iwaki. It was a very interesting presentation. Now we take one question from on-site or online. Do you have any questions? No? Okay, thank you very much. So we move on to the next presentation. I would like to introduce the next speaker, Dr. SHAKTI. Dr. SHAKTI is a researcher, Storm, Flood, and Landslide Research Division, NIED. Dr. SHAKTI will give a presentation on monitoring river flow utilizing high sensitivity seismometers. So, Dr. SHAKTI, the floor is yours.
Thank you very much, Chair and NIED, for giving me opportunity to talk about our research project on monitoring river flow utilizing high sensitivity seismograph during catastrophic flood events. So for this research project, I have been working with Dr. Kaoru Sawazaki, a researcher from Earthquake and Tsunami Research Divisions. So as a theme of this session is catastrophic disaster preparedness and response. So I just would like to highlight the status of natural disasters very shortly. So, so among the natural disasters, so water-related disasters causes severe damage to properties, lives, and it's based on the annual basis worldwide. So if we look the data provided by UNDRR, so we can see about approximately 83 million people were affected by the flood disasters among the another natural disasters. So it's a huge impact by water-related disasters. So the research already warned that the vulnerable people also could increase in coming years. So if we look on other hands in Japan, so the flooding caused by extreme rainfall become more intense and frequent in recent decades. For example, if we look at the annual flood damage cost in Japan from 1879 to 2019, so you can see the increasing the trend of annual damage cost is exponentially increasing trends. So this is the current status of the annual flood damage in Japan. So in these slides, I just want to highlight one example of flood events in 2019. So in this case, the record-breaking heavy rainfall was observed mainly in eastern Japan due to the typhoon Hagibis cases. So many river basins were flooded during that events and for the wider area. So we can see some image, flooded image and destruction image in these slides. So during that events, about 72K homes were flooded, and among them 6.5K were destroyed or damaged. So similar kind of flood events also occurs in many part of Japan, almost in every year. So this animation shows the flooded river basins in Japan from 2012 to 2021. We can see flooded river basins all around Japan. So this is the real scenario in Japan. So during the flood disaster events, so the most important part is the regular monitoring of river flow. So however, there are some challenges to monitor river flow continuously. So one of the important challenges is the regular monitoring of river flow over the upstream basins. For example, in mountainous river basins, we can see lots of observations in downstream side, but we can not see such scenario in upstream cases. Similarly, another problem is the missing of river flow data during the peak flood events. This is another kind of problem. So this image shows one of the example in Typhoon Hagibis cases in Kuji River basins. So this is a real challenges. So there are many practices that have been done since past years. So there are, for example, rainfall runoff modeling, so remote sensing methods. So in some cases, sophisticated camera and radar sensors. So however, they have some benefit and some advantage and disadvantage. So in such cases, we consider the instrument installed for other purposes. So in such doing this, so we use seismological observations, HINET. So this is our new approach to monitor river flow during the flooding events. So this image shows the locations of seismological observations, that is HINET, in a red triangle, and on the blue circles shows the hydrological stations over the eastern Japan. We can clearly see the good network of hydrological stations all over the Japan, but they are the good network basically seen over the flat and urban area. So on the other hand, we can see the locations of the HINET stations, and they are roughly installed to 20 kilometers interval all around Japan's over the flat and mountainous area. So the most important point is that the HINET data is transferred to the data center, and it's only openly available on the internet in real-time basis. So the one important thing in this case is that there are several rivers that have been flowing around the around the seismological stations, especially in mountainous regions where hydrological observations are not available. So that's why we, at first, as a case study, we studied the Mogami River basins, where we can see a lot of HINET stations. So in this, at the first step, we selected the Mogami sub-river basins. We can see in the image. So we can see some HINET stations over the Mogami sub-river basins around here, 2 HINET stations. And we also selected the nearby points from the HINET stations in this study. Then next we performed the hydrological simulations using our models for the Mogami River basins, and we validate our simulated results with the observed hydrological stations. At 3 stations, we can see the simulated and hydrological simulated and the observed discharge matched quite well based on the statistical parameter NSE and KGE. So after that, we extracted the simulated, we can extract river discharge at any point in a river. This is one of the important part. So next, we also extracted the noise data for those stations. So it's a little bit complex. We can see the noise data at different frequency. So the frequency at the noise data at lower frequency looks more smooth rather than high frequency. So we use different frequency of noise and compare with the simulated hydrological data, and we found that the noise data at lower frequency matches quite well with the simulated river discharge. So we perform this for different cases, and then we develop the empirical equations, and then we use to estimate river discharge for the Typhoon Hagibis cases. So this image shows the estimated discharge from HINET and the simulated discharge for the point A and B in this map. So if we compare these 2 discharge, it's they are relatively very close each other. So this is the summary of my presentations. So in this research work, we proposed the use of HINET seismic observations to predict timing and amount of peak discharge in mountainous river basins. The frequency of 1 to 2 Hz noise data exhibited the similar trend to the simulated river discharge value. So what we believe is that this new approach can serve as a valuable reference for monitoring river flow during the catastrophic event, and it's crucial for the flood disaster prevention and management. Thank you very much.
Thank you very much, Dr. SHAKTI. It was a very informative presentation. Now, we take one question from on-site and online. Do you have any question? Okay, thank you very much. So thank you very much, Dr. SHAKTI. So we move on to the next presentation. I would like to introduce the next speaker, Dr. Kozono. Dr. Kozono is a researcher, Volcano Disaster Resilience Research Division, NIED. Dr. Kozono will give a presentation on volcanic hazards and disaster mitigation. Dr. Kozono, the floor is yours.
Thank you very much, Yusa-san. So today I will talk about the volcanic hazard and disaster mitigation based on monitoring and forecasting volcanic activities. So this diagram shows the variation of the duration of volcanic eruption and erupted magma volume. And the diagonal line shows the ice line of magma discharge rate. And we are also showing the various types of volcanic eruption, such as the pyroclastic flow and column-forming Plinian eruption and volcanic explosion, which is the photo of the Sakurajima volcano, and lava flow and Strombolian and Hawaiian eruption. So we can see that the volcanic eruption styles is very diverse and with wide variation of duration, volume, and discharge rate. And this diverse eruption style causes diverse complex hazards. So it is very important to understand the origin of these diverse eruption styles for disaster mitigation in volcanic area. So the magnitude of volcanic eruption, or how catastrophic the volcanic eruption, is represented by this VEI. VEI is the Volcanic Explosibility Index. The VEI is related to the erupted magma volume like this. So for example, the catastrophic caldera-forming eruption corresponds to the VEI larger than about 6. The right figure shows the relationship between the number of eruptions during the 500 years and VEI. So we can see a clear power law distribution. It is very similar to the earthquake frequency. It is famous for the Gutenberg-Richter law. So we can see that the natural phenomena that the smaller earthquake occurs more frequently, or the larger earthquake occurs less frequently. So in Japan, there are active 111 active volcanoes in Japan, and which covers about 7% of the active volcanoes in the world. So this figure shows the VEI against the eruption time, and the different symbol shows the different countries, Chile, Indonesia, and Japan. And we can see that the VEI3 eruption occurs regularly in all the countries. However, in Japan, there have been no VEI5 eruption since the middle 18th century. And also there have been no VEI4 eruption since the 20th century, middle 20th century. So this means that the VEI4 or 5 activity in Japan has been quiet recently. The example of the VEI4 eruption in Japan is Sakurajima and Hokkaido Komagatake eruption about 100 years ago. And also the recent, very recent submarine eruption at Fukutoku Okanova in 2021. One of the famous VEI5 eruption in Japan is the Fuji Hoei eruption in 1707. So this eruption occurred for about 49 days after the Nankai Trough Hoei earthquake, and the Tefra fall blanketed the city of Edo. So this type of eruption is also for the catastrophic event, because this eruption affect the metropolitan area in the future. And the monitoring of volcanic activity is characterized by the multi-observation. And this figure shows summarize the variability of the volcanic observation. And we usually use the seismometers and the tiltmeters and GNSS and sometimes satellite to monitor the deformation and ground vibration due to the magma movement beneath the volcano. And also we are using the visual camera and also the satellites. And sometimes we conduct direct sampling to investigate the magma or gas emission at the surface. So these kinds of various equipment are installed around the volcano, and the observation data are telemetered to JMA and research institute and universities for real-time monitoring of volcanic activities. So I will show some example of our results focusing on the volcano monitoring. And one is the 2011 eruption at Kirishima Shinmoedake volcano in southern Kyushu, Japan. So this eruption was a VI3, and we observed various types of eruptions, such as the subplinian, it's a small plinian, and lava effusion and volcanic explosion. And our institute is monitoring 16 volcanoes, including Kirishima Shinmoedake, by using the Fundamental Volcano Observation Network, which is called VNet. The VNet is consisting of the high-resolution borehole type seismometer and tiltmeters, and also the GNSS stations and borehole broadband seismometers. This bottom diagram shows the baseline length change between the two VNet stations crossing the summit area. So as we can see, in the period before the eruption in 2010, we can see a clear increase in the baseline length, which means that the inflation of the volcanic edifice or the inflation of the magma chamber. And then the volcanic eruption occurred. So during the eruption, the baseline length decreased gradually. So which means that the deflation of the magma chamber, which is accompanied by the magma migration from the magma chamber to the surface. And the right figure shows the 10 days temporal change of the tilt observed by the tiltmeters at VNet station. And we successfully capture the tilt change or the deflation of the magma chamber accompanied by each eruption phase with very high time resolution. So these kinds of observations are used for monitoring and forecasting volcanic activities in Japan. So I also show the example of Mount Fuji. So there is also the dense monitoring system around Mount Fuji. And one of the important observations at this volcano is the activity of deep low-frequency earthquakes. So this earthquake is considered to reflect the activity of the magma or gas movement beneath the volcano. The red points in the right figure shows the hypocenter distribution of the low-frequency earthquakes, and the blue points is for the tectonic regular earthquakes. So from 2000 to 2001, the number of low-frequency earthquakes increased sharply like this. So this became a big news in Japan because we were concerned about the activation of the Mount Fuji. But fortunately, there was no volcanic activity and eruption. And in 2011, just 4 days after the Tohoku earthquake, the magnitude of 5.9 earthquake occurred very close to the Mount Fuji. The hypocenter is here. But however, there was no significant change in the low-frequency earthquake activity. So we need this kind of very dense monitoring station to determine the hypocenter of the deep low-frequency earthquake. So this kind of stable monitoring system is necessary for real-time monitoring of activity at Mount Fuji. So finally, I talk about the volcanic hazard assessment. So the volcanic eruption caused numerous geological and hydrological hazards, such as the tephra fall, pyroclastic flow, lava flow, sometimes lahars, and debris avalanches. So these hazards affect the exposed system in a very complex manner. So it is important to quantitatively assess the volcanic hazard for risk assessment and risk analysis in volcanic area. So I will show the example of the hazard map, hazard assessment of lava flow at Mount Fuji. The hazard map at Mount Fuji was revised recently, and in this hazard map, the numerical simulation of lava flow was conducted under various conditions of vent locations and the magnitude of the erupted volume, and by using the very high resolution topography data. And they constructed many drill maps like this, in total 150. And by merging these drill maps, we obtained a possibility map, which is showing the area where the lava flow for a given time. And another hazard at Mount Fuji, important hazard, is the tephra fall affecting the metropolitan area. So this figure shows the tephra fall distribution of the Hoei eruption. So we can see that the distribution is elongated to us, also in Tsukuba. And the right figure shows a numerical simulation of the Teflon transport and dispersion under various weather conditions all the year. So one possibility map was constructed, as in the case of the lava flow simulation. So the impact of the Teflon fall on metropolitan area is very complex. Sometimes the poor visibility, and also there may be an attack on the electrical lines and water storage, and also the traffic transportation may be largely affected. So we need to assess these impact for disaster mitigation in metropolitan area. So this is a summary. Thank you very much.
Thank you very much, Dr. Kozono. It was a very interesting presentation. Actually, I have one question. I just confirm, what was the VEI level about Mount Ontake eruption 2014?
Eruption is very small. It's, it's
because I just want to grasp that volume. Maybe
it's maybe around the.
Just
I don't
1 or 2?
Yeah, 1 or 2, yes. But so this is a very important point. So the catastrophic, in the case of the volcanic phenomena, even in the case of very small VEI, sometimes the catastrophic disaster occurs.
In the region.
Yeah, in the region. So this is also another topic. So we are trying to install the small equipment very close to the summit by detecting the very small, teeny inflation at the summit. This is also another trial.
Okay, thank you very much. So it means even if it's a very low level of the VEI, it's a very it gave very severe damage to the region now.
Yes.
So it is very important to cite. Thank you very much. So is there any other questions? Nope. Okay. Thank you very much, Dr. Kozono.
Thank you very much.
So next, we move on to the next presentation. I would like to introduce the next speaker, Dr. Gloria. Dr. Gloria is from National Science and Technology Center for Disaster Reduction, Taiwan. Dr. Gloria came to Japan from Taiwan for this session. Thank you very much, Dr. Gloria. And Dr. Gloria will give a presentation on emerging climate crisis and adaptive community-based disaster risk management. Dr. Gloria, the floor is yours.
Thank you. On behalf of NCDI in Taiwan, it's an honor to participate in the spatial section organized by NIED. It was a wonderful opportunity to share what we have been doing in Taiwan. And today, in my presentation, I would like to share 3 key messages. First, how to apply science, information, and intelligence on disaster preparedness and response. Second, how community with well-developed telecommunication facilities and intelligence system can utilize this scientific knowledge and advanced technology in responding to climate disaster. And the last one, what adaptive measures could be taken by remote, marginal, and less developed community while coping with climate crisis. And similar to NIED in Japan, NCDI in Taiwan also did a lot of science-based researches on hazard analysis with the forecasting, earthquake monitoring, as well as disaster impact assessment. And taking typhoon as an example, as you can see from the slide, the researchers, they analyzed the typhoon paths and try to predict where and how many rainfall we are going to have. And based on the rainfall prediction, researchers are able to define the potential landslide of all the flooding areas. And this type of risk information are sent to EOC, Emergency Operations Center, so the commanders can make decisions for disaster preparation and emergency responses. According to the decision makers, and disaster warning messages or disaster alert will be further sent to people living in high-risk area via different channels such as news media, SMS, and social media like Line, Facebook, and Twitter, and also we use cell broadcasting to send the alert And the government at all levels also they follow the standard operation procedure to prepare for and respond to emergencies based on the scientific-based evidence. As you can see from the slides, it's a top-down approach, and the community at the end of the slide, the bottom part, and the community is the end user of all this risk information. And we all know that community are the first responder at the disaster impact area. So therefore, it is crucial to reduce losses and damage if the community is capable to respond to disaster. However, communities and its residents, they don't act like soldiers or robots. And their action might vary depending on what kind of risk information they receive and their characteristic. And first, they perceive the message and then they evaluate the risk they might face. And then they make the decision on whether to take action or not, usually not. And sometimes they do follow the advice from local governments. But most of the time, they just, don't know what to do after receiving all this, risk information, very scientific analysis results, and they don't understand it. So they just wait and see, or take action after disaster happen. And moreover, most of them, they don't trust the information because they don't know how to read it, so that they don't trust it. They think we live here for generations. We understand our environment. It didn't happen before. It's not going to happen in the future. Those kind of things. So it is important that the risk information needs to be transformed to the language that the general public can understand. And the science-based information also have to be downscaled to their neighborhood. As you can see from the previous speakers, all these kinds of scientific map, the hazard map, it was in a larger scale, in a larger region. But the residents, they all care. The slope in the back of my house is going to happen. It's going to have a landslide, and the river in front of my house is going to flood, those kind of things. And so all the risk information needs to be downscaled. And in that case, community is able to make direct connection to their daily life. So to fill the gap between scientists and the local people, it's better to use a bottom-up approach, as you can see from the slides. And the picture on the left was taken when community was doing a town watch activity. They used the area photo as a base map. And then the scientific hazard map was overlapped to it. And they also mark the spots where the historical disaster occurred. So that after checking the potential hazardous places, they were able to understand the environmental risks in their communities. By using the tools such as Microsoft PowerPoint, and the community can produce their own community hazard maps. And they also can discuss where are at the high risks and who should be evacuated. And they also can choose a safer place for their, inside emergency shelter. And later, the community, they began to learn how to put all the risk information on Google My Map so that they are able to update this map annually by themselves. And after understanding their risk, and then their risk awareness has been increased. And as you see from the slide, this is for the earthquake. The green building, that means seismic, first the low seismic risk, and the red one means high seismic risk. And this was produced by the community by themselves. And after understanding their risk, it's much easier to build community emergency response team, and the community can either do tabletop exercise or emergency response drill. And as you can see from those pictures, there is no firefighter or rescue team. It's all the exercise was implemented in the community by the community emergency response team. So the community response team, they also utilize social media such as Line and Facebook to deliver risk information such as accumulated rainfall, flood situation, and response action within their community. And you might wonder, like, what happened after we implement a community program. And the chart on the screen, they shows, the fatalities drop dramatically after the Typhoon Morocco in 2009, which was the time we begin to implement the community project. Although we still have the rainfall was high, but the casualty reduced a lot. And the evidence provide that the plan can effectively reduce losses and damages. However, the kind of approach that might works for the communities with advanced technology capabilities and the telecommunication facilities are well developed in the society. And so for like a remote, marginal, and less developed community, this approach maybe is not suitable for them. So I would like to introduce two cases. The first case is a resettlement site in Iloilo, the Philippines, and most residents, they are urban poor and have been relocated to the marginal area because of flood, urban fire, or urban renewal project. However, they suffer from the annual flood and also lack of income source after being relocated. So we went there, and then we have a project called Plan Back Better. We would like to help them with their develop their climate resistance livelihood, this kinds of approach. And then so that we have a different stakeholder from the government and from the agricultural experts and from the seed company and also the community residents, and then we discuss what kind of livelihood is more suitable for them, and that also can be flood resistance. And so the government provide a public land, and then we invite the agriculture specialists, and we also adopt the local local wisdom of the indigenous people there, and then so that they are trying to do a collective community garden, and so help out the community. They can the garden can be their income resources, and the other half part, and that can be their the vegetable, the fruit they are eating for every day. And then as you can see from the slide, the bed for the vegetable is has been raised because of we need to avoid the flood. And so you can see they have a lot of harvest at the end, and that also help them to overcome the quarantine in the COVID-19. And the last one is the Nepal case, and this is also a very remote and poor villages, and they also has been relocated. So they suffer the annual flood. So we invite like also the marginal group from Taiwan. They are indigenous tribe, but they are good by using the local material to build a bamboo house, and then that is flood resistance. And so you can see we developed two type of houses. One is hybrid house, and the other one is retrofitted house, so that in times of flooding, they can evacuate to the second floor and save all their belongings, and that also lessens their losses. So these are the two different types of adaptive community risk management approach. And thank you.
Thank you very much, Dr. Gloria. I think it is very important to have a perspective to see the hazard and the risk by national side and the regional side or the community side. I think in that perspective, to consider about Taiwan, in the eastern part of Taiwan, it is very like a mountain area, and each small plain is divided by the mountain and the river. So it is very different from the western part of Taiwan and the eastern part of Taiwan. Why did you select the area to test your research in eastern part of Taiwan?
Actually, we select like different parts. Some is very urban area, like you see the seismic risk analysis, and one is like rural area, because in Taiwan we have indigenous people. They usually live in, like as you say, the eastern part, and the way they are doing are very different from the people in the western part. So we need to test different model, and also, although it's all flat, but the time and the type of floods are different. So like you need to try, and there's no SOP for these kinds of community project. It's location based, but you have some principles like a participatory approach and mixed with scientific evidence as well as the local knowledge.
Thank you very much. Why I ask this is because if some disaster happened in southern eastern part of Taiwan, maybe each small plane beside the river is isolated to each other. So it is very important to take care in the community
Yes.
for the disaster risk. So
Yes.
thank you very much.
Thank you.
Thank you very much.
Okay, so we've been receiving several questions on the chat box, but we'll try to answer them at the Q&A session after the panel discussion. But for now, I think I need to introduce the last but not least, the final presenter to present Mr. Yusa of NIED. He's the researcher in the Disaster Information Research Division. So whenever you're ready, Yusa-san, you may start your presentation. Thank you.
Thank you very much, Mr. Matsula. Hello, everyone. My name is Satoru YUSA from NIED. Today, I'm a moderator, and I will make a presentation. And my presentation title is Disaster Information Sharing in Japan Toward Real-Time Situational Awareness. So in my presentation, I would like to present two matters. The first one is the SIP4D, which was developed by NIED as a disaster information distribution platform. The second is about the ISAT. It is an information support chain that collects, aggregates, and provides the information at disaster response headquarters. So first, let's start to talk about the SIP4D. For the beginning, I'd like to clarify the concept and the purpose of disaster information sharing. When the disaster happens, the various organizations work in parallel without information sharing. So based on information only, if situational awareness is different by each organization, effective disaster response will not be achieved. The purpose of the disaster information sharing is to build common situational awareness of the disaster between various disaster response organizations and immediately. It is easy to say, but very difficult to achieve. Like that picture, the common operational picture we call the COP is the situational awareness picture. So over the years, the government has made a great deal of effort to reinforce the resilient function of society. However, the information sharing among the disaster response organization had not been established yet. So therefore, we have aimed to build up shared information platform for disaster management. That's the SIP4D. SIP4D is an information pipeline that enable collecting disaster-related data from various sources, generating ready-to-use information products, and distributing them to disaster response organizations. So, for example, there is a very variety of the information shared from SIP4D. For example, SIP4D itself does not have any information visualization tool like GIS, but each information is acquired and visualized on each linked system. For example, information on earthquakes and floods or the volcanic eruption reported today's presenters by other researchers. And the weather-related information will be shared by the SIP4D. So next, secondly, let's talk about the ISAT. SIP4D is the information sharing system, but the ISAT is the name of the CHIM. Firstly, I will introduce and explain about the background of the ISAT. So I introduced SIP4D, but SIP4D has created information sharing between organizations to be carried out smoothly through the platform. But on the other hand, in the field of disaster response, the information distributed on the system does not reach all the people actually responding to the disaster. Or there are many examples where the necessary information is missing. In addition, since SIP4D is a system which functions only information distribution, it is necessary to know what kind of information is actually needed at the disaster response site and what form is ideal for providing it. So against those background, ISAT was formed to solve these issues. ISAT's official name is the Information Support Team. When a disaster occurred, ISAT is dispatched to the disaster response headquarters in the prefecture. So then, as shown in the slide, ISAT collects the information, number one, and the generate map from those information from the information ISAT gathered on the prefectural disaster response headquarters and combined data from the SIP4D and generate the map, number two. So the information in the blue box on the left is the information that is distributed in SIP4D, and the information in the orange box represents information collected locally by ISAT. And further inform the people of each organization by WebGIS site called ISAT site. That's the number three, provide. So it has the role of providing the ISAT. The role of ISAT is to collect the information and combine the data from the SIP4D and generate the map and provide that map to the disaster response organization via the ISAT site. So the system and data flow is as shown in this slide. So on the left, that automatically acquired information from SIP4D and legacy style information acquired locally but by ISAT are combined, and center part combined and provided right part as WebGIS information. It is key point of the ISAT. So this slide is show the example of the what kind of maps is distributed by ISAT. It's, for example, the evacuation shelter status, not only the those evacuation shelter status, for example, the road closure or the road traffic. And actually, the ISAT site use the WebGIS system, and it means we can distribute not only polygon, point, or line. We also can distribute, for example, the aerial picture of the satellite picture. Also, I said the ISAT provide disaster information mapping products via ISAT site, but actually that is shared to disaster response organization only for the ISAT site. But we also publish disaster information that can be made public through WebGIS site called防災Crossview. ISAT site contain a lot of sensitive information and is therefore not open to the public. So防災Crossview is collection of the disaster information that can be released to the public without those informations. So防災Crossview is linked on the top page of the NIED, and everyone can see the maps about related to disaster. And 24 hours, 365 days. So please check this site and please check the disaster information, and please check the disaster information close to your house or close to your office or somewhere close to your school. So it is very important to check the information via GIS, because with the maps and with the combination of the hazard and, for example, the weather or something, load or the something, a lot of information there are. And we can combine on the GIS, and everyone can check those maps via internet. So it can make you grasp the situation of the disaster, and it can make you grasp the preparation for the disaster. So this is the summary of my presentation. Let me summarize. The first, common operational picture and the situational awareness, COP, is critical for effective disaster response and requires information from a variety of sources. So even if system has excellent function, without the information sharing capability, it may not work in the serious disaster situation. So only SIP4D is not worked well. Only ISAT also is not worked well. The ISAT information gathering, grasping on the local, and the information grasping, gathering by SIP4D, and combination of that and distributing that is very important. So NIED as a national research institute trying to realize information sharing among various disasters. So after realizing information sharing, we finally realizing the information sharing by SIP4D and ISAT. So our next step is to provide decision support in real time. Thank you very much.
Thank you very much, Mr. Yusa. There's one online question.
Okay.
This kind of disaster information sharing system is very important and perhaps demanded by many cities and countries, but someone needs to manage it, maybe finance it, update the information, and maybe do some analysis so that it's useful to the end users. So in the case of Japan, NIED may take this role, which might be ideal case. But how about in situations where there's no organization who can manage this kind of information sharing system? What do you think is a good way to maintain or manage this kind of system?
It is very important question, and it is very difficult to solve problem. But I think, for example, in Japan, we NIED share the information and like maps and those data via the ISAT site or via the Bosai Cross View. But it's a national movement. But not only national movement is okay, I think. For example, Dr. Gloria said in her presentation, the community disaster risk awareness. It is also important. So it is not okay if it's national movement. For example, community-based or just the private-based situational awareness is okay. And for example, the WebGIS is very easy to use, and maybe it's very cheap to use. The cost is very low. So first, you can make a web map to collecting data and to show the map, and let's show that data and let's show that map to your community or to your neighbor or someone, and let's start that movement very small start, and we can provide and we can spread that movement to the community, to the prefectionary, to the regionally, to the nationally. I think that's my answer. Thank you very much.
Okay, thank you very much, Mr. Yusa, for your presentation.
This completes the 7th presentation on catastrophic disaster preparedness and response. I believe that all the presenters were very informative and condensed research results as effective response to actual disasters. I believe that the presentations by these 7 people will lead to following content as a flow. Number 1, how can we information about the disaster itself be observed? And the second, how will those data be utilized as information by disaster response organizations and for the general public. And number 3 is furthermore, what kind of data should be accumulated in preparation for disasters, even during normal time, or utilized for next disaster observation and response. So we believe that studying these processes will lead to the preparing for catastrophic disaster, not as individually as whole studies of our 7 researchers. So now I'd like to break up my time and take a break before panel discussion.
We'll take a 5-minute break. We still have a panel discussion and maybe possibly a Q&A. So see you in 5 minutes. Thank you.
Thank you very much. So thank you very much, everyone. Let's start the panel discussion. So now, based on the presenters, we will move on the panel discussion. In this panel discussion, I would like each presenter to share more information from the perspective of preparedness and response to catastrophic disaster. Not only that, and their international cooperation. I would like to start to ask about each panelist, current research project, and latest information such as overseas expansion and technology implementation. And okay, there's no time now. We will listen to each person's talk in order to their presentation. So first, let's hear from Dr. Takeda. So there was a report on collaboration between NNET and railway operators. I believe that if NNET and the other observation networks and the infrastructure operators cooperate with each other, it will be possible to prevent increase in damage from disaster. So are there any plans or schedule for collaboration with businesses or other than the railway operators? So also, if you have any ideas for which you'd like to collaborate with, please let us know.
Thank you. So we'd like to collaborate with, for example, infrastructure companies. So now we have collaborations with local governments. So we provide offshore data, real-time offshore data, and local government receives the data and estimate tsunami height and inundation. So the information helps local government to anticipate damaged areas and rescue residents. So these collaborations had already started in case of our other networks. So we like to expand the many local governments. We hope. We expect. Yes.
Okay. That's good to hear. Thank you. So collaboration with local government. Okay, so collaboration with local government is also, I think it's very important. So prospecting disaster response, I hope more than anything that the number of disaster victims will be reduced by utilizing the data from SNet and DoNet. So thank you very much. So let's ask the question to the Dr. Kawamata. So there were presentations by, sorry, wait a moment. So by utilizing information from NNET, E-difference, and the seismic motion prediction, in the hazard of earthquake, the 3 presenters presented those materials. So we can create ideas and visions for the future, such as this kind of society is possible with my data, and this is how we can make great use of our data. So is there any idea or something from you? So please tell me if there is.
Thank you very much for your question. Unfortunately, I couldn't mention because of a shortage of time. It's totally my fault. The greatest advantage of experimental study is creation of evidence without causing real damage. So by performing lots of experiments where we can accumulate evidence, and by using this evidence, we can verify and validate the advanced technology, including numerical simulation of like city, regional model. So we can estimate damage status right after disasters, and we can estimate the condition at the time time of occurrence of next disasters. So I mean, so for the next challenge, we are trying multiple earthquake disasters, but this kind of technology can be used to estimate risk estimation against like earthquake followed by tsunami, earthquake followed by fire, heavy rainfall, and so on. So by accumulating lots of evidence, I believe we can make a great technology to make disaster risk estimation in real time or any kind of disasters.
That's great. Thank you very much. So we have great expectation for the future progress of the earthquakes research. So now that technology that we had only thought of as something of the future or something is becoming a reality, I think. And I feel this from each presentation of the 7 presenters. So we are beginning to understand ourselves even more. Yeah, it's very important. Thank you very much. So next, I want to ask Dr. Iwaki, from your presentation, I believe that the prediction of earthquake from the ground motion, such as the hazard assessments and the earthquake early warnings, it's very important information in Japan. Please let us know if there are any example of your involvement with other countries, such as trends or technology development regarding ground motion prediction in Japan. If not, please tell us what the obstacles are.
Okay. Yes. The international collaboration and exchanging the technology and information is very important, and especially for because for earthquakes, large earthquakes do not frequently occur. So if you are looking only at the domestic environment, the experience is not enough. So for example, if I talk about the earthquake early warning, there are many very good established early warning system in the world. For example, in Taiwan and California, in the US, and Japan is one of them. And the system is always tested and being tested and adjusted to every kinds of earthquake occurrence situation that we experience. So it is very important to share the experience with the other part of the world. However, I think the observation system and also the system of issuing the hazard information and also alerts is different from country to country and other region to region from in the different part of the world. So one cannot just copy that one system to another. So that's one difficulty. However, it is always very important and useful to exchange the experience and technology and research results.
Thank you very much. I understand that earthquakes that occur in different parts of the world have their, how do I say, the unique characteristic. So making it difficult to respond in a uniform way. So however, as mentioned in the last comment, I understand that there is a wide range of exchanges of opinion and technical elements. So it is important to continue sharing information with other country. So like this session, yeah. So thank you very much. Let's continue to general research exchange with other country. Thank you very much. So next, I want to ask to the SHAKTI-san. From your presentation, I believe that this research is the major result of the collaboration between the observation and analysis technologies possessed by each division of the NIED. So its effectiveness during typhoon number 19, Ayumi Hagibis, was verified. The report also mentioned the importance of early detecting of river flow in the upper reach of the mountain area. So considering responding to actual disaster, has that system been developed that will issue an alert if a similar situation is observed during the future heavy rain, like a typhoon number 19, Hagibis, Reiwa Forest?
Thank you very much. That's an important question. Yeah, of course, this research is based on the multidisciplinary subject. So that is hydrology and seismology. So it is fortunate that in our NIED we have a different division. So for example, like earthquake divisions, and we have like a flood storm hydrology division. So we try to do something innovative research for the disaster. So I must say that we are at the beginning stage of our research. So in this research, I just highlighted the correlation. I highlighted the correlations between seismic noise data and river discharge. So based on this result, we are more confident that we can continue that kind of research for other river basins, for considering several past events. Once we develop a kind of relationship or equations between seismic noise data and nearby simulated data, then we are much confident that we can predict the especially timing of peak discharge and amount of discharge. So this kind of informations we can deliver in near futures. But as I said, that at this time we are at just the beginning, So we are continuing to do this kind of research for several river basins, and we hope once we develop a relationship, then it will be very crucial for predicting flood disaster in downstream river basins.
Thank you very much. I think the information from your research is very important because the just before disaster happened or the just after disaster occurred is in that time there are very few information. So when information is least available, this research is extremely important from the perspective of the filling information gaps. So there is no information in that time, but your research and that data is filling that gap. So it is very important to the disaster response for not only us, but also for the prefectural government and not also the prefecture, it's for national. And I hope if you can show your data to the general public or for the disaster response organization, I want to cooperate with your data and ISAT site or the Bosai Cross View to expand your the data to the public.
Yeah,
so
that's what we are expecting.
Yes, that's good for NIED and that's good for us. So thank you very much. So Next, I want to ask to Kozono-san. So today, our session's title is the Catastrophic Disaster and Preparedness. So it has been pointed out of the eruption of the Mount Fuji and the Nankai Trough earthquake may occur in tandem in maybe same time or the 1 week gap. So if that happens, I feel that real catastrophic disaster will occur. So in order to reduce disaster damage as much as possible, so please give us your opinion on disaster prevention and mitigation in the event that you find yourself in such a situation.
Okay, thank you for your question. So as you pointed out, the coupling of the big earthquake and Mount Fuji eruption, it may be one of the worst scenarios in Japan, maybe. So I think we have to, in my mind, that what we have to in our mind is that how we can continue the monitoring of Mount Fuji even after a big earthquake. So as shown in my today's talk, I show that continuous monitoring is essential for assessing the activity of volcanoes. So we have to keep a very stable monitoring system even after a catastrophic case. And also, I think another point is that we must assess the effect of the tephra volcanic hazard to the transportation between the big cities, for example, the West and the East Japan. Because sometimes the tephra fall in the wider area disconnect the transportation lines such as railway and roadway. And also sometimes the lava flow from the Mount Fuji may reach the Pacific Ocean. So these hazards may disconnect the logistics and the human flow. This is very important in the case of the catastrophic scenario because we have to transport many things between the big cities. So we have to assess the effect of the volcanic hazard on the infrastructure, road or railway, so by using the experiment and numerical simulation, so more quantitatively. So that's our big topics in volcanological hazard assessment and vulnerability assessment.
So thank you very much. So there is the national road #1 is under the hazard of the Mount Fuji, I think. So the transportation and that's very important for the hazard preparation. So I understand the importance of the prediction and responding the disaster based on the cooperation with each organization. So volcanic eruption maybe say to be infrequent, you said. So, but once they occur, they can be a catastrophic disaster, even though it's a VEI1 level for the regional. So I look forward to the strengthened cooperation that the new law will bring. Yeah, thank you very much. So next, I want to ask to Dr. Gloria. So this time, Dr. Gloria participated from Taiwan. And I feel that Taiwan and Japan have similar types of disaster like earthquake, landslide, or the flood, everything. And ways in which their societies deal with disaster very similar. So if you have any plans or ideas for the future cooperation between Taiwan and Japan in terms of responding to disaster and or the developing technology. So we would like to hear from you.
Thanks for the questions. Taiwan and Japan both having very experience significant earthquake and typhoons. And in Taiwan, usually we have like 3 to 4 times of typhoon making landfall to Taiwan. in our record, but for the past 4 years, we didn't have one until last month. And the reason is like, each time when the typhoon was approaching to Taiwan, and then it make a U-turn and go to Japan directly. So that, it shows like, it's like, thank you so much. But just kidding. Like, both sides, we have a very long history of mutual learning, no matter it's from the disaster instance and the lesson learned or, the scientific research result. And Japanese disaster researchers and Taiwanese disaster researchers, both sides has very frequent exchange. I knew some of them just, visit Taiwan a few times ago. And so, like, this was a very good foundation for the cooperation. And looking ahead, I think our cooperation could focus on utilizing the modern technologies and tools to enhance the resilience and the coping capacity of local government units and the community as well, since they are as I mentioned, they are the first responder to disaster events. And especially, now because of climate change, so in the context of climate crisis and the catastrophic disaster, that's the targets we can focus on. And beyond, like, sharing research results, like today, I, in my personal opinion, like join pilot projects across borders, and that could elevate our, the collaboration among both sides, like Japan and Taiwan, to a new height. Thank you.
Thank you very much. I believe there are many areas where Japan and Taiwan can cooperate in disaster response. So not only at the government or the local level, but also the local community level, as you presented. So NIED also currently conducting such research, especially in Japan, disaster prevention in local communities in area with small population, for example, the mountain area. Is also, we think it's a very big topic. So I hope that various exchanges regarding disaster prevention will continue between our two countries and our two organizations. So thank you very much, Dr. Gloria. Thank you. So now, I would also like to say a few words about the disaster prevention information, so which is the subject of my research. For example, from the perspective of the distributing disaster prevention information, it is extremely important to know how to quickly provide information brought about by the latest research to people who are not feeling well. So it is also very important to consider the form of the information depending on the organization and the position of the person who needed the information, the scale of the national, governmental, prefectural, local. So the ISAT activities that I introduced involved directly communicating with the people in need of the information during the disaster response situations. So we would like to mutually develop our research by providing feedback to everyone and about knowledge we have gained and usefulness of our disaster responses. So thank you very much. Okay, now it's time. Thank you for everyone. Through the panel discussion, it was very short time. I'm very sorry, but I think we were able to see the latest information on each research and the future prospects. Utilizing this research, we will continue to prepare for the catastrophic disaster, not only Japan, in Taiwan, and every country of this world. So now that the time has come, I'd like to conclude the panel discussion. Mr. Matsura, please move to the Q&A session or closing.
Yeah, thank you, Mr. Yusa, and thank you for the panelists for the fruitful discussion. We've been receiving some questions online, actually, but we're actually ran out of time. Maybe we can pick up one question that's overarching to all the presentation or the research field of our panelists today. So I'll choose one. Yes. So the question is, well, it's actually appropriate to kind of close this session on catastrophic disaster, because the question is asking whether there are like key issues or points to consider, especially when studying or doing research about catastrophic disasters. Is it just an extension of your existing research, or is there something unique or some special elements that you have to consider when we talk about these mega disasters, the catastrophic disasters? So I want to give maybe 20 or 30 seconds to answer to each panelist. I know it's a challenge, but hopefully you can give us some pointers to answer this question. So we may start from that if it's possible.
20 seconds.
20 seconds.
Okay, 20 seconds. Okay, so in the case of volcanic eruption, so yes, that's a very important question because the caldera forming eruption is the different kinds of topics. So we have to extend the research topics for especially for the catastrophic phenomena. This is my opinion.
Thank you very much. So next, SHAKTI-san, 20 seconds.
Yeah, it's very difficult to answer within 20 seconds. But of course, for the awareness and the response for the catastrophic disasters, we have to work more collaboratively, because if for example, big earthquake happens, there could be a chance of flooding, like a tsunami, building damage. So if we work together, then maybe we can have some idea to tackle this kind of problem. That's what I want to say.
Thank you very much. Next is Iwaki-san.
Okay, my opinion is that the research for catastrophic disaster is not just an extension of the usual research, because we have not experienced yet. So that means we don't have the observed data, or so we have to use the simulation or maybe experiments to make the estimation. Okay, that's my question.
Thank you very much. So next, Kawamata-san.
I think at the first stage, we don't need anything new, but we need to accumulate the evidence, as I mentioned. And after that, I think we can find something new. So we can make big challenge together by accumulating data from any researcher in the world. I think it's the first step.
Thank you very much. From my opinion, to learn or to know the future or to know the catastrophic disaster is to learn history. History can teach us what happened in their history. There were very huge catastrophic volcanic eruption or the very huge earthquake, and we have the record by book or by very old report. So to learn history is to learn catastrophic disaster.
Taiwan and Japan has been experienced a lot of disasters. So for the small-scale disaster, I think both sides are fine, no problem at all. But for the bigger one, the next one, and I think that should that is the focus we should address, because it's across border and it requires a lot of coordination and collaboration among different stakeholders, and so that the worst scenario, disaster scenario, that should be taken into account in our future planning. Thank you.
Catastrophic disaster influences very wide areas, so and many local governments. So we must keep the wide area observation network, and during the event of a catastrophic event, we keep running. We have to keep running monitoring and obtain the data, and the data will be provided to GMA and other stakeholders. Thank you.
Okay, so thank you again to the presenters for first keeping the 20 seconds rule, and for giving us very insightful presentations, and of course the panel discussion as well. And of course, Mr. Yusa, thank you for the great moderation. And of course, the Secretariat, the organizing team, and of course the participants here on site and online as well. We have actually several questions coming on the chat, but we'll try to distribute the questions to the researchers that you addressed, and we'll try to come back to you with questions. So with that said, I think we're at the end of this session, so I would like to close this special session. I thank you all again very much, and wish you a great evening. Thank you.
Thank you very much, everyone. Thank you.